No? Okay. Yeah? All right. So, hi, everybody. This talk I gave 2 weeks ago in Milan as a dry run, right, to see that it would fit in the time and everything. And what I discovered is that most of the people in my audience were quite young, and they were unfamiliar with any language that was kind of older than Java or Python. So we ended up stopping and explaining things, and so it ran a long time. So I'll try to go a little more smoothly through it, and if there are questions, we can handle them at the end. So what we're going to try to talk about are the ways that we represent software, and what we really try to do is step up from machine language and assembly language and all that ugly stuff that we used when I was a kid, and represent software in ways that are more meaningful to the human and to enable humans to communicate that information to others, whether that's in something that's non-executable like a use case diagram, or something that can be directly transformed into an executable program like a state transition diagram. We'll kind of cover the spectrum, but we're going to focus on the idea that you have to design your languages in a certain way, whether they're text-based or graphically based, and that there are some guidelines for communicating them from one person to another. All right. So if we go back, we can go back to Ada Lovelace, if you suppose, but really, I think if we go back into the 1940s with the very earliest computers that were being used, of course, by both sides during the Second World War to figure out how to launch rockets and do those kinds of things. But the things that go back to that time are flowcharts and transition diagrams and, of course, assembly code. Assembly code was a big step up from standing at the machine and flipping switches. If you've ever been to the Computer History Museum, you can go there and flip switches, which is, not a happy way to spend your day if you're trying to get any work done. But we moved in the 1950s to higher level languages. They, at the time, were called third-generation languages, right? Machine language, assembly language. And then Fortran and Algol and COBOL. And there was a big debate at the time about those languages because they didn't compile very efficiently. And machines were slow, memory was limited, and so there was a tremendous amount of work that went into writing the compiler as much as for the language design itself. And they weren't quite as fast, but they saved human time. So Jean Sammet wrote a book in the 1960s. She was president of ACM at one point and worked for IBM. And she put this Tower of Babel diagram there, which includes kind of all the languages that had been heard of at the time she produced the book. And the tower actually includes English, because there's been this long-standing dream that you can talk to the computer and say, this is what I want. And Warren Titleman in the 1960s wrote some software called Do What I Mean, and the idea that you could tell it what you want. And we're coming back to that now with the rise in artificial intelligence, the idea that you can say what you want to happen, and things like Copilot pop up and do their best. And of course, they're not quite there yet, but they're definitely an indication of where we are going, where we might be. So why are there so many languages when you look at that diagram? Well, first of all, in the early days, people designed languages like Fortran and Algol for numerical mathematical computation, and they were binary. And people designed COBOL, right, starting in 1958 or so, for business, and used decimal machines, right? So you had two families of machines that IBM built, and at the time they had about 70% of the computing market. So basically everybody in large companies ran an IBM system. People wrote extensions to languages for real-time systems. People wrote simulation programs. They wrote games. So, when you look at the languages used for games today, there are things like Lua, which, I never learned. But if I were working for a games company, then I certainly would. There also were evolving programming techniques. So we started with algorithmic languages, and then there was a whole school around functional languages, of which Lisp is probably the best known. And then we went to object orientation with Simula and Clue. Most popular and widely used languages, you have Java and C++ and Rust, all of which follow an object-oriented programming style. And of course, people had to deal with things like concurrency and networking, and most languages evolved sets of libraries to deal with those kinds of things, rather than designing a new language. But, down in the lower right-hand corner, it says vanity. People like the idea that they designed a programming language. So in 1958, when the first version of ALGOL was invented, there was a guy named Jules Schwartz who worked for TOW down here in Southern California, and he didn't quite like ALGOL 58. So he created his own version, and it's known as Jovial. Jovial is Jules' own version of the International Algebraic Language. So, people really like the idea of, designing languages that model the way they think for the problems they want to work on. And there's some excellent examples of it. Pascal is really as good an example as any, because it was intended for education and fit into the mind of Niklas Wirth. So, but certainly a fairly large number of these languages that have emerged, they're like, top 40 music, right? This is the popular one, and it was written by this person. And indeed, you can go look on the web, and you'll see that every month there's a top 15 or top 20. What are the 15 most used programming languages last month? It's like your own hit parade. That certainly is a factor. So if we look at things, there are a lot of different kinds of programming languages, and we won't go through all of these, but I listed a couple of examples in each category. So object-oriented languages, and research languages, teaching languages, systems programming languages. So those of you who may remember the lengthy design process that came up with Ada. Anybody remember that? Yeah, that was like 40 years ago now, right? They came up with 4 candidate languages, and the Ada as a winner came, really evolved from Jean Ishbia's Langage d'implémentation des systèmes, LIS, and then, of course, there's this whole pile of interpreted languages, of which Python is clearly the leader these days. And we have languages that are used on the web. Maybe you don't think of those as programming languages. They're rather markup languages or display languages, but HTML and JavaScript, PHP. Data management, I designed a language that was basically an extension of Pascal to handle relations as a data type. So I put my name in there on that, on one. SQL, of course, is used to this day. It was designed in the 1970s at IBM San Jose, and lots more. I mean, we could go on indefinitely, because we have our own Tower of Babel of languages today, which is considerably larger than Gene Samet's from the 1960s. There also are some notable failures, and there's a lot of intellectual or financial investment in some of these languages. When ALGOL 68 was designed, Professor van Wijngaarden from Amsterdam sort of took everything that he wanted to put in a programming language and proposed that it be called ALGOL 68. Well, of course, nobody ever wrote a compiler for it. So nobody ever really wrote a running program in ALGOL 68. IBM, when they introduced the 360, right, the idea was to do away with these two families of machines, one for business and one for mathematical programming. So the whole 360 family was intended to support all kinds of programming, from small computers to large. And as part of that effort, they designed a language called PL1. Nobody here has written the program in PL1. You have. I'm impressed. Okay. That's a separate talk. So great. So PL1 was implemented at IBM, and it took 7 years for them to get a compiler that more or less worked. So that was kind of a big undertaking. And of course, at the time, they were still building OS 360. Many of you know about this indirectly from having read Fred Brooks's book, The Mythical Man Month, right, where he described all the various issues that he encountered in trying to get those products out the door. All right. So now the other thing that came up along the way, all these languages that we've talked about were really aimed at professional software developers, people who studied programming or had a computer science degree, although it was really somewhere into the 70s before you could get, at most places, a degree in computer science. But the idea, again, of people, non-programmers, end-user programming, being able to do their own thing was an important step along the way. And what came out most visibly are what's called fourth-generation languages, right? So as we move up another level, and there were a lot of them. Okay, now some of them had a big following and they had good commercial support. Nomad is a very good example of that, and Power Builder. I've used for many years a tool called FileMaker, which has its own little scripting language. It was put out originally by Apple and is now still supported by what was a subsidiary of Apple. So Focus, Progress, a number of these languages, and they all had kind of the same mind behind it, which is conversational access to relationally stored data. And then it was just a matter of taste or which salesman got to you first. But all these languages in that category had the same flavor. And we see in those languages really the genesis of what we call low-code and no-code development today, of which there are, again, a very large number. If you were to go out and search on low-code, no-code tools, you'd get to 150 and going. It's a big number. And of course, it's dominated by a very small number of products like Mendix, a Dutch company, and by the tools that Salesforce has built, originally Force.com, and then subsequently they came up with two different languages at different levels of abstraction. And again, people are writing programs in these languages to deal with Salesforce applications. So if you're writing your customer relationship management system or your sales management system and you want to extend it and generate certain kinds of reports, then those languages are really well suited to that. And there's a big volume of those languages, and many of them are offered commercially for sale. Oh, you're running Salesforce and you're paying some number of dollars a month. For a few dollars more, as the title of the movie was, you can have these additional add-ons, and they're sold by independents. We also have WYSIWYG tools, what you see is what you get, that are used for building web applications. The best known of these are Wix and Squarespace, but what goes on more commonly are content management tools. Again, you're not writing in a procedural programming language, though there's a procedural programming language sitting underneath it. So I can design a website with Drupal And if I need to tweak it, fine. There are hundreds, maybe thousands of modules that are add-ons that work in the Drupal framework. There are themes that allow you to customize things. And if you want to go beyond that, there's PHP. So you can go in there and script it. More popular than Drupal, of course, is WordPress. And WordPress, somebody told me, and I haven't checked it, but something like 40% of the world's websites run on WordPress. That seems like a big number, but I don't have the data to tell you otherwise. In any event, if you want to build a website quickly, you can be up and running with either Drupal or WordPress in 20 minutes. It doesn't take much programming skill. It takes some design talent and those kinds of things. So what this boils down to is that there are a whole lot of ways that people can go about expressing what they want to see in an application or in a website. Right? And these range from low-level machine processing things to highest-level non-procedural languages and other kinds of notations that show you what you want. There are all, I can't quit this slide without mentioning spreadsheets. But you can write macros for Excel, and people make huge bugs in them, because the people who are writing the spreadsheets are the accountants and the finance people, and they're not usually programmers or trained in programming. And so, when your bill is off by 2 orders of magnitude, it's probably because someone made a mistake in an Excel macro. All right, well, there are also a whole bunch of graphical languages. I mentioned early on things like transition diagrams, but in the 1970s, we saw a number of these things emerge. Larry Constantine and Wayne Stevens and Glenn Myers created structure charts. That was published in IBM Systems Journal in 1974, and it's a way of representing the architecture of a system and the information that flows back and forth between the various components of the system. It's not at all dynamic. Right? It doesn't support distributed systems or networking because it was 1974. But it was an example that if I wanted to show somebody how I wanted to architect my system in that era, the structure chart was great, okay, because I could see what information was being passed back and forth. I could separate global data from local data, all those kinds of things, right? And I could see the modular structure of my system. So it was very powerful. I could take each one of those modules and decompose it, right? Because I have subdiagrams, or I could attach code to each of those modules. So what we did, I started a company called Interactive Development Environments, and we were one of the first 100 .coms. And we built this product called Software Through Pictures. And this actually is an IDE shirt. And it's pretty old, but it's still there. Sort of no holes in it. But what you can see on the slide is that we're able to represent the various modules and the information being passed back and forth. And you can have things that are notation, that they're modified by the module or that they're passed back and forth. But what's interesting in the middle is this little box that pops up called module decomposition. And if you click on that, you get another window, and you can either use a program design language that is a high-level description of what you want that module to do, or you can write code. Okay? And if you write code, you can export it. So we actually were able to use the structure chart model as a way to generate the skeletons of programs, and if somebody wanted to go further, they could go in there and fill in the code for the module itself. Okay. TimeNet was a PetriNet tool, so people used Petri nets because they had concurrency features. And so here's a tool. And what you might be able to see is that these tools were built to run on engineering workstations. So we were very good buddies with the people at Sun Microsystems because every time people bought software with their pictures, they bought a Sun workstation to run it on. So they liked us a lot. But TimeNet, they built a custom user interface. I'm not sure what that ran on. David Harrell at the Technion in Israel created a notation called state charts, and then started a company where they built a tool to support state charts in that company. And that product was called StateMate. And this is a very high-level diagram showing the different kinds of diagrams that you could put in creating a state chart. For those of you who use Eclipse, after they worked on the programming environment, they set up a group that built a modeling framework. So you can actually use that modeling framework to build various kinds of modeling tools. And I just showed you one simple example. Another one that I didn't show you, but I could, is there are a variety of entity relationship diagram tools. So entity relationship diagrams for database modeling were created by Peter Chen in the 1970s, in the first issue of ACM Transactions on Database Systems. And entity relationship diagrams are very widely used. And our tool, as well as many others commercially, had graphical representations, and they could generate schemas for your favorite database management system from the graphical model. So, when you go to design a programming language, what is it that you do? What are the issues that you face? Well, a lot of people have given some guidelines for how to design programming languages, whether it's to support a particular application domain or a particular methodology, or your own personal preference. Do you like to start everything on a new line? Do you force indents? How do you feel about semicolons? All these things factor into the way that people design languages. Time isn't going to permit us to go through all of these things in detail, but it's all in the paper. You need certain kinds of foundational structures to deal with different kinds of domains. So if you're doing string handling, Fortran wasn't so good for that. People built specific languages that were aimed at string handling, going way, way back to things like Snowball. But people also designed languages to support their own cognitive processes. And then they piled on a lot of libraries. If a language became popular, people wrote modules and themes and application programming interfaces and all kinds of other stuff to support that language and make it more useful. The best example of that these days is Python, right, which has a huge number of libraries aimed at machine learning and AI. So Tony Hoare wrote, the objective criteria for good language design may be summarized in 5 catchphrases: simplicity, security, fast translation, efficient object code, and readability. Interestingly, 2 of those had to do with the internals, not about the language itself. Klaus Wirth, who's known for Modula and for Pascal and a few others, gave a very brisk description. You have to have a clear idea of how a language is going to be used, right? Because you need to select the right primitives for it. That's how you come up with your basic abstractions. And he made the point that you got to leave stuff out. If you put everything in, you end up with PL1, okay, or Ada, and it's too big to implement and too big to use. And he made a big point about that. Tim Peters, who's a guru on Python, gave a list of things in the Zen of Python. And what's interesting is that even though it's a different kind of language, there's an overlap. Okay. And then I took my own shot at it some time ago, I put together a book called Tutorial on Programming Language Design, and in that I listed these 5 things. For me, abstraction and modularity come first because they're the way that you separate the issues and deal with them. So language design goes on, right? It's an ongoing activity as we sit around. Maybe some of you are designing your own languages as we speak. Others may be planning to do so or have recently done so. And now these new domains are leading to new languages. So, are the tools that are being used to support AI, is the AI going to design its own language? Or are there going to be notations that support AI? And of course, quantum computing has a different computing model, and because things can happen like Schrodinger's cat, how do you express that kind of notation? And I'm quite sure that will lead to new language advances. So that's it. That's my hometown. And an unusual, rare, sunny summer's day. So this finds me, among other addresses, and I'll stop there and take any questions you may have.
And yes, we have a little time for a few questions. So, Peter.
Thank you for the walk down memory lane. I'm probably one of the few people here that is old enough to remember some of those things that you were talking about. In particular, you mentioned that Algol 68 was never implemented. I think we should take a look at the Algol 68 homepage that refers to several ports of previous compilers that have been resurrected. Another point that a bit more serious is you characterized Ada as a failure. There's been a 2023 standardization of a new version of Ada, which is more than 40 years after it was first developed. And I think a language, even though perhaps the original aspiration of Ada of being the language that, in particular, the Department of Defense was going to use for all its software was perhaps overambitious. But to call it a failure, a language that survived for 40 years and with Ada Spark is also a topic of current use.
Well, I don't know how many people use it, but in fact, I was on one of the committees that evaluated the candidate languages, and I was on the it's an American standard that evaluated that DoD directive and recommended canceling it because so many exceptions were requested to writing in Ada. There were only 2 commercial implementations of Ada made available, and when you consider the tremendous amount of money that was spent on it over many, many years, I would call it a failure. Is COBOL 2023 or Fortran 2023? Those are both out now also. How many people are using the new version of COBOL, I wonder? So,
but with Ada, for instance, I'm familiar with the DDC Ada compiler that was developed in Denmark. I was actually a consultant on the project, which was a commercial success and used in the military in the Netherlands, and was actually the second compiler that passed the validation suite based on formal semantics development. So some of these things that you're saying, I can't really relate to.
Okay. Well, let me put it a different way. How many people have written a program in Ada? More than I thought. Good, thank you. Thanks for your questions, Peter.
Hello, thank you for the presentation. It was a nice, it was very interesting. Since you are proposing a historical perspective, I think that I will ask the obvious question, that's what about the future? What do you think about the next steps if you like to play the futurologist? In which language will you bet? or something like that?
Yeah, so that's a dangerous question, you know. So, you know, one of the things that we know is that most people like their first programming language. And because it's the way that they were trained to think about programming. So whether it's Python or JavaScript or Fortran or something. Which is why we have a 2023 version of Fortran and a 2023 version of COBOL and so on. So what's coming in the future? I hinted at that, and I think we're going to have new languages to support AI applications, and we're going to have new applications to support quantum computing, and maybe we're going to get something that deals with crypto in an unusual way, or encryption or security. Rust has some of those elements, and maybe it'll get extended in a way that will be popular. But I think that it's very hard at this point, not impossible, very hard for a new language to gain critical mass. And you know, so much is open source as well. So you know, you can have a niche language, and we have a lot of those. But to have something that, when I ask the question, and everybody raises their hand, that's going to be hard to do, I think, because we've become more decentralized. Does that help? All right, what's your thought? All right. All right, good, thank you.
All right, well, let's thank Tony one more time, and then we'll move to our next topic.